Dear students, in the last class we have studied about the steady state stability limit of the synchronous motor drive, in which we have studied that the maximum torque is given by T is equal to T max sin delta, where T max is equal to 3VE upon axis omega ms, or it is a plough torque where the torque is maximum or sin delta is equal to 1 or delta is equal to 90 degree, and the torque can be increased up to the pull out torque by increasing the angle delta. Now we have to study about the dynamic stability. If load torque TL is applied, suddenly motor may lose synchronous. Even if load torque is less than the maximum torque, if any sudden change in the load torque, it is fall under the category of dynamic change or dynamic. We have to study the dynamic stability of the motor. If load torque is increased suddenly, the motor may lose synchronous and the maximum torque, if even though the load torque is not the maximum value at the T max, but the change in sudden, then the dynamic stability of the induction motor has been affected. So when load torque is changed suddenly, whether the motor will retain synchronism or not can be determined by examination of the dynamic behavior of synchronism. So in that case, we have to study about the dynamic behavior of the motor. Under transient condition, a synchronous motor can be represented by an equivalent circuit by replacing E by E dash, XS by XS dash, where E dash is the voltage behind transient reactance and XS dash is the reactance before disturbance. So by this study, we can see that the voltage behind transient reactance E dash, it is given as V minus JIS into XS dash, and the motor torque can be represented as T is equal to 3VE dash upon omega ms into XS dash, or T max dash into sin delta, where T max dash equal to 3VE dash omega ms XS dash. E dash is the voltage behind transient reactance and XS dash is the reactance, transient reactance for disturbance. So this is the torque equation, or the maximum torque T max dash represent the maximum torque in the dynamic conditions. So torque balance equation as T is equal to TA plus TD plus TA. The motor torque supplied the load torque plus dynamic torque plus acceleration torque TA. This equation is just like similar equation as a fundamental torque equation which we studied in the first unit, where TA is known. TA is acceleration torque can be given as Kj into d square delta upon dt square, when dynamic torque Td equal to Kd into d delta upon dt. When we put in this equation will become Ta will become Kg d square delta upon dt square, Td will become Kd into d delta upon dt. T, which is the synchronous motor torque, which can be given as minus T max dash sin delta plus TL, which is a load torque equal to 0. So by solving this equation, the solution of this equation, the nonlinear differential equation, we can obtain the variation of delta with respect to time, or we can calculate the desired parameter of studies by from the solution of this equation. So this is about the dynamic stability and dynamic behavior of a synchronous motor drive. Now after this, the next topic is the braking of the synchronous motor. As we have know that synchronous motor is run in the synchronous, means stator field speed and rotor field speed are the same, which is synchronous speed. Any of the change in both the speed, it will lose the synchronous. So motor can work in the regenerative braking only at synchronous speed. Therefore, regenerative braking cannot be used for stopping or deaccelerating a load, because in the regenerative mode, motor may be work as a generator, as a synchronous generator, and to work as a synchronous generator, the motor speed is the same as a synchronous speed. Means the speed cannot be reduced in that case. So regenerative braking is not possible in the synchronous motor, because the speed cannot be reduced. Motor and synchronous motor can be worked only in case of synchronous. Either it can be worked as a motor or it can be as a generator. Any reduction in the speed are resulting the loss of synchronous. So regenerative braking is not possible. Dynamic braking is obtained by disconnecting stator from the source and connecting it to a three-phase resistor. This is the circuit for the dynamic braking case, where the stator has been disconnected from the source and it is connected through a resistor R, dynamic braking resistance R. So by connecting it to three-phase resistor, machine work as a synchronous generator and dissipate generated energy in the braking resistor. Now the motor work as a generator and the loss of generated energy in the rotor resistance. In per phase equivalent circuit of a per unit speed K is shown in figure. Per unit speed is given as K is equals to omega m upon omega ms, or it should be less than 1. It is less than 1. So K is a per unit speed, and the per, according to that, the circuit is made is a per unit circuit, per phase equivalent circuit, that it is represented by KE, KXS, where K is the omega m upon omega ms. So by this circuit we can calculate the braking current ISB. ISB is braking current. Current in this resistor, it is equal to the KE is the source divided by total reactance of the circuit RB square plus K into X square. Braking power is gained by 3 into ISB square into RB. The value of ISB can be here. Similarly, the braking torque can be represented as TB, which is can be given as braking power P upon omega ms. So PB upon K omega ms is the braking torque. By putting the values of current, or putting the value of current here, we can give the expression of braking torque 3 RB square KE square omega ms RB square plus K square into XS square. So this is all about the braking of a synchronous motor drive. Thank you.